After the topic on how to evaluate trig functions with two angles being added together, like sine of 30 plus 45, now we're going to be looking at what happens when you have a trig function of 2 times an angle, like sine of 2 times 30 degrees. So here we have what are called the double angle identities. They are called the double angle identities because if you see an angle like sine of 60 degrees, you can actually think of that as 2 times 30 degrees. So you could compute sine of 60 by doing 2 times sine of 30 and cosine of 30. Now usually these proofs are not actually used for computing angles though, because for the most part we're able to evaluate everything like sine of 60 degrees from the unit circle as it is. However, we will use these more extensively for proving statements. So if you see sine of 2x, you'll want to replace that with 2 times sine of x and cosine of x instead. So these are definitely used more for proofs than for computation. Now the cosine one is the trickiest because we have 3 different versions or 3 different possible substitutions you can make. So you'll want to base that on what you are working towards. So what's on the other side of the proof or the statement that you're trying to verify. If you see that the proof you're working towards only has cosines in the answer, for example, then I would recommend using this second choice. If you see that the proof only has sines in the answer, then I would use this last function. And if you do see a combination of the two, then it might be a good idea to use the first one, but this is probably the one I use least often. And then there's another double angle proof for the tangents as well. One good thing to know about these when you're performing proofs, every time you see a sine of 2 times something or a cosine of 2 times something, you should always do the substitution. This is definitely one that you want to take every opportunity you get, unlike the Pythagorean identities where sometimes it's not a good idea to replace using those properties. These you should always keep an eye out for and substitute right away at the first chance. Sometimes you will get a question that asks you to use a sum or difference identity to prove one of the double angle identities we just looked at. So to do this, the idea is not to use the double angle identities themselves, but instead to break something like 2x down as the sum of x plus x. So since x plus x adds up to 2x, we're actually going to evaluate this or see where this property comes from by using a sum or difference property from the last video. Well, if you're following the sum and difference properties for cosine of an angle plus an angle, then you should get that the next line is cosine of x, because my first angle is x, and then cosine of x again, because my second angle was the same thing, so cosine of x. And then the sign flips, so it becomes minus, and then sine of the first angle and sine of the second angle. So that's applying the sum and difference identity from the last lesson. And then having cosine of x times cosine of x, we actually usually write that as cosine squared. The same way we would write sine of x times sine of x is just sine squared. The next step to recognize is that by looking at our target proof, what we're trying to get to, there aren't any cosines in this expression. And we still have a cosine squared here. So what we can do is apply one of our Pythagorean identities and replace cosine squared with 1 minus sine squared. I'm not changing anything here, so I still have that minus sine squared. And then negative sine squared and negative sine squared, these are actually like terms. So think of it as negative 1x minus 1 more x. So negative 1 minus 1 is negative 2. And then that concludes the proof, because now we have what we were working towards. So this was not a proof using the double angle identities. This is instead telling you why we're able to make this substitution. We have just proven that cosine of 2 times x will always be equal to 1 minus 2 times sine squared of x. So if you ever see a question that says use a sum or difference identity, don't use the double angle identity proofs. You're just trying to prove why those statements are true from the last slide. And then you'll get a breakdown from the earlier properties, the sum and difference properties. Now that we have proven why those double angle identities are true, well, we've proven one of them anyways. We can prove the others as well if we need to. But now that we have proven that they are true statements, sometimes the question will just say perform a proof like that sine of 3x equals sine of x times 3 minus 4 sine squared. So now I'm saying you are welcome to use the double angle identities since we have just shown that they are true. However, you'll notice that sine of 3x is different than saying sine of 2x. So right now, we actually don't have our setup to use a double angle identity. So these properties often get combined with the sum and difference ones. So I'm going to instead rewrite sine of 3x as sine of 2x plus x. Since 2x plus x equals 3x, this is a true statement. I can still break it down that way. And then here I'm going to be combining the sum and difference property with the double angle properties to perform this proof. So my next step, when you're using the sum and difference for sine, we end up with sine of the first angle, and then cosine of the second angle. And then the sine function uses the same plus or minus, so plus, and then it flips to be cosine of the first angle and sine of the second angle. So that's performing the sum and difference identity. Now I have sine of 2x. So now this is what the new lesson is about. It's about recognizing the sine of 2x's and cosine of 2x's and making a choice to substitute. So the sine of 2x choice is just 2 sine cosine. If those two things are equivalent, we will always want to replace sine of 2x with 2 times sine times cosine. But don't forget that I still have that times cosine, so I need to have another cosine out here on the side. Now the cosine of 2x1 is a little bit trickier. So what we want to do is look at what our target proof is going to show, and it looks like we should only have sines in our final answers. So we're going to look for a cosine of 2x substitution that only has sine in it. So in this case, I'm looking to replace cosine of 2x with this third option because we don't want any cosines anywhere in our answer or anywhere in our proof. So I don't want to use the other one since they have cosines in them. So always look at what your goal is to determine which substitution is best to perform. So here I'm going to replace that cosine of 2x with 1 minus 2 sine squared of x. But don't forget to leave off the other times sine of x part that we have. Since we left those other numbers being multiplied outside, let's go ahead and actually multiply them in now. Now this is just 2 times sine times cosine again. Since we're ending up with a cosine times a cosine, that becomes cosine squared. This is not a distributing case. Be careful about that. There's nothing being added or subtracted here, so that's just one multiplication. Now in this other one, I do need to multiply twice because I'm going to have sine times 1 and I'm going to have the sine times negative 2 sine squared. Since there's a plus or a minus, I need to multiply this through twice this time. So 1 times sine and negative 2 sine squared times sine. We're getting close to being done, but I still have a cosine term in my expression. So what we want to look for here is a way to replace cosine squared of x with something. And this is going to go back to our older properties, the Pythagorean identities. So I'm going to substitute cosine squared with 1 minus sine squared. And again, the reason I'm thinking to do that is because I know that my target proof, or the target for my proof, should not have any cosines in it. So every time I see cosines, I'm looking for a way to replace them with sines. Performing that substitution has set up another multiplication. So now I need to do 2 sine times 1 and 2 sine times negative sine squared. So be careful about your distributing, whether you should distribute at all, and actually changing the exponents like sine times sine squared to sine cubed. And everything else from here is just going to be some combining like terms and maybe a factoring step. So we've changed everything to sines, which is good. I do see a couple like terms. For example, we could combine the negative 2 sine cubed and the negative 2 sine cubed. We could also combine the 2 sine and the 1 sine, so that would be 3 sine of x. Minus 4 sine cubed. And then for our final step, we do have a GCF here. So it looks like they factored sine of x out of everything. So we're going to factor sine of x. This is the GCF taken out. So if I do 3 sine of x and I take sine of x out, that leaves behind a 3. And negative 4 sine cubed divided by sine is negative 4 sine squared. Don't forget to always check your factoring by just multiplying it back out and seeing if your answer works. Because sine times 3 is 3 sine, and sine times negative 4 sine squared is negative 4 sine cubed. But in this case, we knew we were done because this was a proof, and now my work matches what I had on the other side of the equation. And now for a solving example, we're going to be solving equations, so still trying to find our answers in the interval 0 to 2 pi, so that means including 0 but not including 2 pi. And now we're going to start having to perform a double angle substitution in these sometimes. So here we see that cosine of 2x that we know what we want to replace. This is the tricky one because we have to make a choice about which substitution to perform. So always look at what else is in your equation. We know that we're going to have to factor at some point. So to make the factoring easier, we want everything to be the same trig expression if possible. So in this case, I'm going to try to replace cosine of 2x with something that only has cosines in it, which means we would like to use this substitution right here this time. We don't want to end up with sines and cosines, so I don't want to use that one, and we don't want to use that one for the same reason. So we're going to replace cosine of 2x with 2 cosine squared minus 1. We also need to move everything to one side of the equal symbol, so I'm going to go ahead at the same time and move that negative cosine over and write plus cosine of x. And I'm going to go ahead and move that negative 1 over to make this plus 1. Remember, this is not a proof, so you are allowed to work on both sides for these. So now we're trying to find specific angles where this statement will be true. After the substitution and moving everything to one side, we're going to look for any like terms we can combine or anything we can do to kind of simplify or clean up this expression a bit. So I see 2 cosine squared and a positive cosine, but the negative 1 and the positive 1 will cancel each other out. So I don't have a constant left anymore this way. So now we've gotten to a point where we can factor because I only have 2 terms. I have this term and I have this term, and they both have something in common. So this is that GCF. You should always look for a GCF before trying the other factoring techniques. So if I take cosine out of the first term, I'm left with 2 times cosine of x. And cosine out of the second term leaves me with a 1. Please check your factoring. Cosine times 2 cosine is 2 cosine squared. Cosine times 1 is cosine, so make sure it matches if you went backwards a step. But once you have your factoring done, you can split this up into 2 different equations. So I'm going to have cosine of x equals 0, and then 2 cosine of x plus 1 equals 0, which makes it a lot easier to solve. In fact, the first equation is done. There's nothing else to do there. But here I need to subtract 1 and then divide by 2. So we're going to be looking for where cosine of x equals negative 1/2. To get your final answers for these, this is where you look at your unit circle, or if you already know the values offhand, and you want to say where is the x coordinate for cosine equal to 0. That happens twice on the unit circle. It happens at pi over 2 and 3 pi over 2. And then this is also a cosine statement, so where are your x coordinates equal to negative 1/2? That happens at 2 pi over 3 and 4 pi over 3. So these 4 angles are between 0 and 2 pi, including 0 but not including 2 pi, and they can be plugged in to make a true statement out of the original equation. There's no extraneous solution or anything here because we don't have any tangents or secants or anything. So that's it for the notes. If you like this video, be sure to like, subscribe, or comment.